we finish up chapter 2 by extending what we learned in the last section about probability to more complicated scenarios and conditional probability. So let's start with an example. In the Powerball lottery, there's 69 white balls to choose from, and they're going to pick out 5 of them. So you get to pick 5 different white ball numbers chosen from the set of 1 to 69. And then there's also a separate bin of red balls, which each one has a number from 1 to 26 on it. So you have to choose 5 white ball numbers and choose 1 red ball number. And to win the jackpot, you have to match all 5 of the white ball numbers and also the red ball number. We want to find the probability that you hit the jackpot in Powerball. All right, so there's 2 things that need to happen here in order to hit the jackpot. You need to select the correct 5 white balls that match the 5 that they pulled out, and then you need to match the 1 red ball. All right, so first let's find the probability of matching the white balls, all 5 of them. All right, so we want to find how many possible outcomes there are, or sample size here. In other words, how many ways could the host of the, I don't really know how the lottery works. How many ways could the machine spit out 5 white balls from this total set of 69? Well, there's no replacement. It's not like you can select a 2 twice. And so the number of ways that they can select any 5 balls from this set of 69 would be 69 choose 5. Right, this is a combination because the order that they select them doesn't matter. You don't have to match them in a particular order. So this number, remember, is going to be something like 69 factorial over 69 minus 5. That's 64 factorial times 5 factorial. That's our sample size. And the 5 that you select have to exactly match the 5 that they select. So there's really only one desirable outcome here, and that's the outcome that your 5 balls match theirs. If you only had to match a few, then there'd be lots of different outcomes, but if you have to match all 5, then only one outcome is going to work for you here. So the probability that you matched all 5 of the ones that they pulled out would be 1 over 69 choose 5. That is this number here, 1 over this number here. And that number, by the way, is roughly 0.00000088. All right, which really means the probability of just matching the white balls is 0.0000. I think I missed a 0, actually. I think there's one more 0 in there. 0. That's very small. This probability is ridiculously small, but remember, this isn't even all you have to do, because you have to match the 5 white balls, and you also have to match the 1 red ball. So what's the probability that you matched the single red ball? This is a little bit easier. This time the sample size is just 26. Well, you could think about it as 26 choose 1 if you wanted to, but 26 choose 1 is just equal to 26, right? They either chose the 1 or they chose the 2 or they chose the 3 all the way up to choosing the 26, right? 26 choose 1 is just equal to 26. And again, the desirable outcome is that you picked the same one. So there's only one possible desirable outcome here. So the probability of matching the red ball is 1 over 26. But we need both of these events to happen. We need this to happen, which is very unlikely, and we need this to happen, which is still pretty unlikely. It's roughly 4%, maybe a little smaller. So how do we know the probability that actually both of those events will occur? Well, for that we need to use the probability that independent events occur. So suppose that 2 different events, E and F, are independent of each other. Independent means something similar to what it means in the set theory chapter. It means the outcome of one event doesn't depend on the outcome of the other, which in this case, in this example, it matches that, right? Whether or not you match the 5 white balls is not going to depend on whether you match the red ball and vice versa. So these are independent events. Well, the probability then that both E and F occur is going to be equal to the probability of E times the probability of F. That is, as long as your 2 events are independent of each other, you can find the probability that both events happen by multiplying them together. Okay. And so for us, what this means is that the probability of winning the Powerball jackpot is going to be equal to the probability that you match all 5 white balls, and also multiply that by the probability that you match the red ball, right? Because both of those things have to occur. So what is it? It's 1 over 69 choose 5 times 1 over 26. It's very, very small. I can tell you roughly what it is. 0, 0, 0, 0, 0, 0. 342%. This isn't even as a decimal. This is a percent. This is the percentage chance of you winning Powerball. It's tiny. Don't play the lottery. It's so unlikely that you will win. Okay, so the important thing to remember here is that this rule only works when your events are independent of each other. Not necessarily going to be the case when they're not independent. But let's look at another example. Let's say we want to find the probability that a randomly selected adult Let's say we're given the fact that the probability that a randomly selected adult subscribes to Netflix is 35%. So this is saying 35% of adults subscribe to Netflix. I made this number up. I don't think this is true. Just for the sake of the problem, let's suppose that that is the case. What is the probability that 4 randomly selected adults all subscribe to Netflix? Well, let's try to think about this as independent events. So our 4 independent events here is in the first case, let's say, choose a random person. Let's call that person A. And find out if they have Netflix. Our second event is going to be choosing a different random person. Choose another random person. We'll call that person B. All right, then we'll choose a third person. Call them C. And choose a fourth person, person D. Now the probability that person A subscribes to Netflix doesn't depend on whether the second person subscribes to Netflix. Right? These 2 people are just 2 random people. The probability that one of them has Netflix doesn't have any impact on whether the other one has Netflix, and that's going to keep going all the way down the line. So we can actually use that rule from the last section 4 times, or maybe 3 times, to get that, well, the probability that the first person that you chose has Netflix is 35%. If you wanted to, you could rewrite that as a decimal, right? You can rewrite that as 0.35, or you could rewrite it as a fraction if you like, 35 over 100. Either way. The probability that the second person also subscribes to Netflix is also 35%. I'm going to go with a fraction here. If you want to use a decimal, that's okay. Similarly, probability that the third person subscribes to Netflix is 35 over 100, and the fourth person is also 35 over 100. So the probability that the first person does, and the second person does, and the third and the fourth can be found by multiplying together each one of these probabilities, which means that the probability that all 4 subscribe to Netflix is going to be equal to 35 over 100 times 35 over 100 times 35 over 100 times 35 over 100. That is 35 over 100 raised to the 4th power. Or if you prefer to do this with decimals, 0.35 to the 4th power. Okay. So again, we could use that rule because these events were independent, but they're not necessarily always going to be independent. Sometimes the probability that one thing happens will depend on whether something else happens. So for this, we want to refer to something called conditional probability. So suppose E and F are both events of some sample space, and we need to assume in this case that the probability that F happens is greater than 0. In other words, it can't be the case that F is an impossible event. Then the conditional probability of E, given that F occurred, is given by the following equation. So we read this as probability of E given F. So the probability that event E happens, given that we know that F happens, and we can find it by finding the probability of E and F divided by the probability of F. Now, if these events happened to be independent, then we could use that rule that we had before, say that this is going to be equal to probability of E times probability of F, and then cancel. But generally, these do not necessarily have to be independent of each other. So events E and F are not necessarily independent. And that's when we're going to most likely be using this formula. So let's try to see what that means in an example. So suppose we flip a coin 10 times. What's the probability of getting exactly 1 heads, given that the first flip came up tails? So we know the probability of getting exactly 1 heads. We did a similar problem, I think, in the last video. Just in general, when we flip a coin 10 times, the probability of getting exactly 1 heads is equal to, all right, the denominator is the total number of outcomes. So when you flip a coin 10 times, there's going to be 2 to the 10 outcomes, heads or tails for each spot, right? Heads or tails, another heads or tails, all the way down to the last one, heads or tails. So 2 options each time. So our total number of outcomes is going to be 2 to the 10. And we want to know, out of all these different sequences of heads and tails, how many of those have exactly 1 heads, meaning 1 heads and then 9 tails? Well, you could either have heads in the first spot and then tails in all the others, or you could have heads in the second spot and tails in all the others, or you could have heads in the third spot. All right, I'm not going to make you listen to me for all of these, right? But the heads could go in any one of these 10 spots. And so there's 10 possible allowable outcomes here, right? Except they're giving us more information here. They want you to find the probability of getting exactly 1 heads, given that the first flip came up tails. So essentially, they really want you to rule out one of these scenarios here. They want you to rule out the scenario that the first flip came up heads, because they're telling you that didn't happen. They're telling you that the first flip came up tails. So really, this should be 9 over 2 to the 10. But let's make sure that tracks with what we saw in the theorem above, the conditional probability. The conditional probability tells us that the probability of getting exactly 1 heads, given that the first flip came out tails, should be equal to, running out of space here a little bit, should be equal to this. The probability of E and F, the probability that both things happened, the probability that we have exactly 1 heads and the first flip was tails, divided by the probability that the first flip was tails. Okay, oh, I see I made a mistake up here now. Right, so not only do we have to eliminate this first scenario here where we started with a heads and then had 9 tails, we also have to change the total number of the sample size in the bottom here. Because if we're saying that the first flip came up tails, there's not really 2 to the 10 outcomes, right? In this case, we're saying the first flip guaranteed to come up tails, which means there's only 9 spots left. And each of those 9 spots could be heads or tails. But we're guaranteeing that the first one came up tails. And so there's really only 2 to the 9 total outcomes here. Okay. So we want to make sure that the probability we get using this formula ends up being 9 over 2 to the 9. All right, so let's go through this. The probability that you get exactly 1 heads and the first flip came up tails is going to be 9 over 2 to the 10. That's what we had up here above. Before we had said that we're not necessarily requiring that the first flip came up tails. We're just saying if you flip a coin 10 times, what's the probability that you get exactly 1 heads and the first flip was tails? So those are those 9 different scenarios we're looking for, and we have a total of 2 to the 10 possibilities. But we're going to divide that by the probability that the first flip came up tails. Well, the first flip has to come up either heads or tails. They're equally likely, so this probability would be 1/2. So this is going to be your total probability, 9 over 2 to the 10 divided by 1/2. we could rewrite this as 9 over 2 to the 10 times the reciprocal. Right? Dividing by a fraction is the same as multiplying by the reciprocal. So we can multiply by the reciprocal, in other words, multiply by 2 over 1. And this will simplify to 9 over 2 to the 9, which is what we wanted. That matches what we had up above. So we'll see some more examples of conditional probability in the exercises.